We are here today for the webinar symposium that is hosted by M-Star, Enterprise Deployment of CFD Models. So we're going to be talking about simplified workflows for setup and running an analysis. We, again, are just thrilled that you've taken the time to be with us today. We have 4 presenters that are going to be sharing their expertise with us today. On the schedule that you saw, our first presenter is Cory Quammen from Kitware. We'll have Masoud Ahmadi, next Reza, Ebrahimi, and we'll finish up with John Thomas. I'm going to just do a quick introduction for Cory, and then we'll jump in with him, and then when he's done, we'll move on to our next presenter. If you want to drop them some questions in the Q&A during the presentation, please feel free. Otherwise, we're planning to have the Q&A mostly encapsulated within each presentation. So if you have a question for that presenter, go ahead and ask them during their presentation. If there's time at the end, we'll do additional Q&A, but we'll see how it goes. So far, so good. Let's start off with Cory. So Cory is a technical leader at Kitware Incorporated, where he heads the development of ParaView, one of the most popular scientific visualization and data analysis applications available today. He also leads client projects to provide customized visualization and analysis solutions based on Kitware's open source platforms. More recently, he has been working on pairing visualization technologies with web applications to make simulation technology like M-Star accessible for broad user bases. He holds a master's degree in computer science from the University of North Carolina at Chapel Hill. So, Cory, with that, I hand the time over to you.
All right. Thank you so much, Amber. And I just want to make sure everyone can see my screen. Great. All right. So, yeah, like Amber said, well, thank you first, Amber and John, for organizing this seminar and for M-Star for sponsoring it. Like Amber said, I'm Cory Quammen from Kitware, and I'm going to tell you about Aeroflow, which is a turnkey web application that enables enterprise-wide access to M-Star CFD simulations. I want to give you a little bit of background about Kitware first. So Kitware is really a software and R&D services company. We have customers in government and industry and academia, and we have many, many projects, more projects than people that work for the company most of the time. We have 209 employees worldwide. That's within the US division, with our European division. We have offices across the US. Kitware was founded over 25 years ago. And in that time, we've had sustained growth. We've become a 100% employee-owned company. Our expertise is deep in a number of areas. 2/3 of the folks that work here have master's or higher degrees. I think it's about 1/3 have PhDs. And really, we've been founded on an open source business model primarily, and that entails supporting these vibrant communities that support open source, freely available, and extendable software. And we have a strong commitment to open science and science and R&D in general. So one of those areas of expertise that I have and others on my team is related to 3D visualization and analysis on the web. We've been doing this for over 15 years, bringing in visualization, 3D visualization to the web, using our open source platforms like VTK and ParaView. In that time, we've developed numerous web-based visualization applications developed for our collaborators and partners and customers. And recently, in the last few years, we've noticed there's been a high demand for simplified web-based simulation workflows. And an example of one of those is shown on the right. This is a web viewer for the Moose framework to view some simulation results from there. So why are people interested in providing simplified workflows on the web for their simulation software? Right? So they've worked really hard to make great physics-based models, simulating lots of important physics. And oftentimes the software might not be easy to use or easy to download, or it takes a lot of expertise to use. M-Star CFD is not one of those. It's a tightly integrated simulation software with really great tools like M-Star Pre M-Star Solve and M-Star Post that put all those tools together in a sensible, easy to use way. It's great desktop software that you can deploy on your on-premises PCs or even in the cloud via remote desktop. But even with that kind of distribution model, you run into some limitations. Like if it's on a PC in your organization, there's only one seat in front of that PC, especially on Windows. Only one person can use it at a time. Or cloud access to remote desktops, isn't always the greatest user experience. It's pretty good and scales pretty well. But, maybe there are some other ways to make your simulation technology more broadly available. So that's really one of the goals behind Aeroflow, what I'll be talking about throughout the rest of this talk. A second goal, and maybe just as important, is improving accessibility of simulation software to people who aren't experts in it, basically. Even when it's straightforward to use, I've used M-Star pre to set up a model and run it with success. I'll be honest, I didn't know what I was doing. I'm a computer science background without any kind of physics or modeling expertise, but I was able to kind of get it to run, right? That's the idea, is you want people like me who only know a couple of things about what I want to model to be able to use the software, right? I'm not going to know anything really about Reynolds numbers or certain boundary conditions, but I understand length of time, right? How long do we mix fluids in a bioreactor or something like that? What temperature works best, or what kind of rotation speed on the mixer is needed? Those things are meaningful to me, and if I had some controls that I could change, I can do simulation and get some answers about whatever physical scenario or mixing or drying or whatever I'm trying to do. Those parameters are meaningful to me. I can get some information back. I need to make some kind of decision in whatever process I'm developing. So the second goal is to make simulation more accessible to more people, not just the computational experts. So here's a summary slide. Those are basically the two guiding motivations behind the development of Aeroflow: how to make simulation more broadly available to more people, and accessible to more people with different skill backgrounds. So we, over the last year and a half, have prototyped and developed Aeroflow and made it available for people. And Aeroflow is tightly coupled with M-Star CFD. It's a web application that offers a simplified simulation interface, and installation is pretty easy. I'll touch on all three of these points for the rest of my time here. So starting out with Aeroflow is a web application, right? So simulation workflows on the web, I mentioned, are popular, and there's a lot more interest in that these days. Everything's moving to the web. I'm sure you do banking, pay your bills. We've been doing that for a very long time, watching TV even. Basically, everything's on the web because web browsers make access to software easy and universal. Like I can look at websites like I'm doing right now, talking to you through my web browser on my laptop or even on my mobile device. It's everywhere. It's kind of becoming the default operating system in a way for software development. And so Aeroflow is doing exactly that, but for bringing M-Star CFD simulations to the web. So where does Aeroflow run? Right, so we're not a software as a services offering. Aeroflow is software that you would download and install on some web server that's controlled by your organization. That could be either on the premises or in the cloud. But anyway, you retain total network security and access and all that kind of detail. And I know you're doing sort of sensitive simulations. Users would connect to this server that's hosted on your network with just a standard web browser. They're very capable web browsers today that can handle the kinds of 3D visualization we're doing, or chart drawing, etc. The only real requirement that we would impose over any other kind of normal web server would be you would need a GPU capable of running M-Star CFD simulations. makes sense, right? We're an interface running M-Star, but we're also using that GPU to generate the images that are sent back and displayed on the client. So if you're already running M-Star CFD somewhere, installing Airflow at that same location using the same GPU resource is a kind of straightforward no-brainer to do. Right. So next, I'll move on to or how we're simplifying simulations and presenting that to the users. So a lot of you here, I assume, are very familiar with simulation workflows in general. We have a couple of main steps here, including setup, simulation, and analysis. The setup, you're taking some geometry, you are setting some parameters, you are dictating things like how certain geometry might move, like a mixer rotating. Some simulation tools have a whole meshing step, but we don't have to do that. M-Star CFD. Then there's the simulation component. We're actually executing, running the physics, getting the results. Finally, looking at doing some analysis in the end, looking at the data, seeing what it tells us. Right. So that's your typical simulation workflow. And again, M-Star Pre makes it easy to set up certain scenarios, or a lot of scenarios. But that's not really the focus of what Airflow provides. We're going to let the experts do that, who have the training and knowledge, kind of encapsulate that into what I'll call simulation models through the rest of the talk. And all these images, thanks to a paper from some of the folks at M-Star, of modeling mass transfer in the stirred microbioreactors. So as a computational scientist, you have all these tools under your belt and can do amazing things really fast with M-Star. I thought of an analogy. I hope it's a good one, but we're giving you the tools like a painter. Think of painting. There's a lot of tools available. You've got paints. You have to mix them to get the colors you want. And there's a whole technique of how to apply them to the canvas, know what you're trying to paint in the first place. There's a lot of knowledge and know-how, right? If you're good at it, in the end, you get some masterpiece. We don't want everyone to have to do that. Not everyone can do that. We want to simplify that and maybe turn that into more of a paint by numbers kind of thing, right? That most people can do. And they've got some flexibility to put some artistic spin on things, right? So in this case, we want to provide curated simulations from the full power and capabilities of M-Star CFD, and just expose the few important parameters, some of which I cited earlier. CFD experts are going to know and maybe talk to intended users, what parameters are important to expose. And then those users can adjust those, run simulation, look at results, make some changes, see how those changes improved or made things worse. But that's the main idea. We're simplifying the workflow for the end user. And Airflow provides a pretty straightforward way to do this using text templates that will define these simulation models. So if you've ever had to set up an input deck text file, it's very similar to that. So in the end, we get something like this. Our setup and simulation and analysis workflow looks much easier. We just have 3 parameters here that are exposed. We change those. We click run. In Airflow, once you click run, then you switch over to a visualization mode, and this will show you the results as they're computed live, and as new results come in, it will update. By default, it will update to the most recent time step. So if your model is, if it's fast enough to simulate, which often it is with M-Star, you can see it evolving in real time in front of you on your web browser, which is pretty awesome. And of course, in analysis, we provide some charting capabilities to show plots and some reporting capabilities as well to generate reports. So here's a few screenshots of the interface. This is what maybe, say, your field engineer, if they're some user of this technology, might look like. Oh, I'm sorry, my lights in the office turned off. Here I am again. From the field engineer perspective, this is what it would look like. So I've got these numbered here. So if you start out looking at your simulation models, They're presented here with an attractive picture and description telling you what they are. Those are both things that you would provide to define these. And then you set up, once you've chosen the simulation model to run, you set those parameters using the simplified interface that we provide, and click Run Simulation, and you look at the results on the right. So it's pretty straightforward, kind of this three-step workflow. Results that are computed previously can be loaded and visualized later. There's a list of those that appears for every simulation model that you have defined. For the computational scientist providing these simulation models, there's just a few things you have to provide. So one would be your M-Star pre-model, which you have anyway. Then this logo, this attractive picture that we showed there, and the summary text. It's just a little text file. Then there's three kind of important files that actually control things and decide what user interface to present. One is just a tiny little file in JSON format, which is easy format to learn if you don't know it already, and it's pretty human readable. These specify the default parameter values. There's a template that defines the exposed parameters. So we saw those three parameters with sliders before. It's kind of a more specialized language, but you write one of these, it's pretty straightforward to write them. And then there's a mapping file from whatever parameters we've exposed and named to the underlying name in the M-Star software. So that covers what Airflow is and the simplified simulation that it offers. I'll just talk briefly on installation process. We made it pretty easy to install on a standard Linux system. So we provide it as a Linux Docker image. It means it comes with all the dependencies, everything that's needed to run. You just point Docker at it and go. It's basically the short story of it. There's some configuration you need to do. You get a server-specific license file for Airflow. There's some networking configuration to do to open ports so that people can use it on your network and that kind of thing. But all within normal system administrator IT type responsibilities. And then there's an abbreviated set of commands here to show you how to load this image and then run it. Pretty straightforward. I'm not a super smart web guy either, but I was able to get this running. In fact, I was even able to get this running on Windows using the Windows subsystem for Linux, which I really didn't know anything about, in just like a couple hours. So it's pretty straightforward. And so that is my overview of Airflow. If you want to find out more, we have a website available. If you scan this QR code or type in the link here. And I think looks like I'm well within time. So I've got some time for questions. Let's see.
If you want to put questions in the Q&A, feel free to type your question in and Cory can address it there.
Cory, I have one question, if you don't mind, just while we're asking. So I know there's Train, which is available on GitHub, which you can download. And that's, I think, used to kind of run some of these web-based services. How is Train different from Airflow?
Right. So Tram is one of our, it's a French word, and I think I've heard it as Tram. I'm sure I'm missing some subtlety there, but it is one of the open source platforms that Kitware does most of our work on. It encapsulates really this 15 years of web experience of doing some basic communication between web browser and the backend kind of rendering service, but then adds on top of that a nice Python-based user interface layer that makes it pretty easy to write nice visualization applications using only Python, both developing the 3D rendering aspect but also the user interface. So Airflow uses Tram to do the interface development and uses its client-server coordination capabilities and we packaged it up. And a little bit different model for us is that this is a product that we license and charge a licensing fee for, but provide support with that.
Yeah. So in principle, could someone use TRAM, I know I'm pronouncing it wrong, to replicate a lot of the functionality of Aeroflow? It might be hard without some handling, but in principle, the open source is there. But Aeroflow is a developed product that can pick up off the shelf.
Right. Yeah. So if you want it off the shelf and don't have to write it yourself, Aeroflow is perfect for that. But you're right. All these things are based on open source technology that you can grab and use right now if you want.
We did have a question come up in the Q&A, but I think you answered it. Is Aeroflow an open source or paid software?
Yeah, we do charge a license fee for this. Yep.
Okay, well, if there's no further questions, maybe that will wrap up our first presentation.
Thank you. And thanks everyone for attending.
Thank you.
All right, thanks so much, Cory. We are now going to move on to our second presenter, Masoud Ahmadi. Masoud is a computational modeling engineer at Amgen, where he applies mathematical models using M-Star and STAR CCM software to optimize drug development processes, including mixing tanks and bioreactors. He has a master's degree from Tarbiyat Modares University and a PhD from Michigan Technological University. So, Masoud, we hand the floor over to you.
Appreciate Amber for the introduction. I need to first acknowledge M-Star and this webinar for providing the stage for us to present this idea. I'm happy to share my screen. Let me check the screen sharing. Is it visible right now?
Yep, looks great.
Awesome. Yeah, thanks everyone for joining this webinar. I'm Masoud. As like we are providing here, it's a enterprise deployment of CFD models, and I'm going to share with you how we are transforming the process development with utilizing an end-to-end mixing analysis toolkit, which is going to be replacing traditional wet mixing studies. So here is the outline of my presentation here. It has three parts. I'm going to talk about what we are doing and answering why we need this type of tools. And then at the second part, we are going to answer the what question. What are the things that are that we have developed and are using at Amgen? And at the last part, I'm going to answer how we are deploying the on-demand simulations with the guidelines, and also presenting you with a case study that shows how any user can use our mixing analysis toolkit. So for the first part, I'm going to cover some context, what is the challenge, and how we are trying to come up with solutions for these challenges. So as you, all of you might know, the mixing tanks are in pharmaceutical an essential part to the process itself. Having a homogeneous blending between various components is very essential. If we have a proper mixing, it ensures the product quality, efficacy, and continuous production, and also to avoid the deviation throughout the process. So traditionally, at-site wet mixing studies, although they are indispensable because we need them for the validation purposes, but they come with a set of challenges. They are typically resource intensive, especially for large mixers that you need a lot of material to do the wet mixing studies. And also they come with a high operational overhead. And the most important thing is that they need days of dedicated personnel time for them to be completed. On the other hand, we have ad hoc simulations that although they are very valuable for new designs, let's say a new tank or a new skid, they are still very valuable for those type of simulations. But the challenge for this type of simulation is that they are not on demand. They are not easily or readily available for the users, and they need to be deployed by a modeling expert. As Cory described, for someone who doesn't have the expertise in the modeling or CFD, they would find it hard to approach this type of solution, and still there is hours of dedicated personal time needed for this type of simulation. And modeling experts should put hours of dedicated time for getting the results for this type of simulation. But here at Amgen, instead of waiting for days for the at-site wet mixing studies or hours for ad hoc simulations, we have enabled on-demand analysis. So here we have a high-fidelity computational model thanks to M-Star for doing the simulations for the mixing tanks. We have qualified the model to ensure the quality and also repeatability of the data. The models that we output and give the users to get the results is data-driven, and it is generated based on a surrogate model based on the CFD results. And anyone throughout the Amgen, every engineer can go to this application store and run on-demand simulation of mixing studies. At this part, I'm going to discuss what is the model on the back end that M-Star has helped us a lot for developing, how we have qualified these processes, the workflow, and also how the data-driven model is leveraging the CFD results to generate the surrogate model. And all of these are enabled by having a high-performance computing and on-demand licenses from M-Star. And also at the end, I would present how we are democratizing all of the results on a web page. So as you might know, the M-Star is actually a very powerful tool for covering the key physics that are happening inside the mixing tanks. The transport equations are being solved by M-Star, fluid flow and species transport, and also the free surface also can be tracked with the M-Star tool. The FSI, or the two-way fluid-solid interaction, is also covered in this model. DEM and also mean age analysis are the other type of models that are covered by the M-Star itself. On the other hand, we have also encountered different types of mixers. As you can see on the right, the liquid-liquid mixing by the reciprocating disk mixers is shown, as we know that the fluid flow is going to affect the solid, and also the solid is going to affect the fluid flow. Also, we have encounters requesting the dissolution type of simulation for the rotating impeller mixers, and M-Star is very capable of covering all this type of mixers throughout the Amgen processes. So to ensure the quality, or how qualified the model is for our process, we have developed or internalized an SOP, which is based on ASME VNV40, that it is based on the risk of the model. As you can see here on the middle of the graph here, the risk index is based on model consequence, which can vary from risk to business or risk to directly to the patient, or its influence, which can be just supporting information. It can be the sole or authoritative sources of information for the model. Based on the risk index, we have a series of verification, validation, applicability, and procedural activities that we take based on the risk, that we test the model based on those and get the qualification done. The other piece of the puzzle is having version control and CI/CD pipelines for the model. We have this model on the GitLab, and also it has more than 200 unit tests for a near complete code coverage. Also, thanks to M-Star, the other part of this solution, or having the qualification done, is the computational engine itself. It goes to automatic testing before each release, and make sure that it solves a benchmark solution for the mixing tanks before being published and used by the users. So as I mentioned, we have developed a fully automated surrogate model generation. And as you can see in this fully automated end-to-end workflow, what are the steps that we are taking? We need to first provide the workflow with the CAD files, physical properties, and working conditions that we need to have for a specific tank. Then it is fed to a sampling method, which is using an adaptive sampler for selecting the points that are essential for having a surrogate model for that mixing tank. Thanks to the advanced API of the M-Star, execution of the simulations are automatic, and also the results are published, and we get to a general surrogate model. And this loop here, it goes on until a threshold is met, and then automatically it also pushes the results on an app that every engineer can reach and also use the results. The other piece of enabling this type of simulations or on-demand simulation is having a high-performance computing, because we need to have a large number of DOE points that are needed to be studied by the CFD engine. So Amgen has built a high HPC platform, which is using AWS. And because of having the on-demand licenses from the M-Star, we were successful in executing more than 100 parallel DOE simulations for the process optimization per day. This is a phenomenon in terms of how quickly we can have a new tank introduced to the app. So the last piece of the puzzle is to publish the results on a platform that can be accessed by everyone throughout the Amgen. So here at Amgen, we have an in-house app store which is called Cosmos. It enables the power of modeling in the hands of the users. It can be integrated with any programming language and off-the-shelf software. It helps democratizing the model deployment. And also on top of everything, it also provides the user with a previous run history that they can go back in time and see what type of simulation they were having and what type of results it was acquired by any previous user or themselves. At the last part, I'm going to discuss a little bit about how we deployed these on-demand simulation. What is the in silico guideline, and how everyone or every engineer throughout the Amgen can have access and use our toolkit. So for having like removing the user variability of the process and also ensuring the repeatability of the test, this in silico mixing guideline was necessary to bring consistency throughout the blanket of the Amgen. It shows the users what is the standard procedure for each tank before being deployed on the app, and what are the steps that are taken for each tank before being published on the app itself. So it gives confidence to the users in terms of even getting to know the details of what do we mean by the vortexing, what is the shear rate signifies, and other parameters that are reported on the app. At this part of the presentation, I'm going to present you with a use case, which is a standard procedure for every engineer that wants to know more about the mixing performance of a tank. Here, I'm showcasing a case which an engineer can go to this web page app, and first step is to find the maximum agitation rate that doesn't exceed the performance or doesn't create the vortexing issue inside the tank. So they can go and select the agitation rate type of modeling, and they can go have a wide range of agitation rate, and they would choose the lowest working volume and also low density and viscosity. This ensures that the results are for the worst case scenario that can happen throughout the process inside this tank. After setting these numbers, they can run the program, and after a couple of minutes or seconds, the results are going to be published on the app. When they go to the vortexing tab of this app, they can find out what should be the maximum agitation rate that they can run the mixing tank and reduce the probability of having a vortex inside the tank. By selecting this 175 RPM for this tank, then they can go and change the type of study that they want to have. For example, they would go to the mixing condition and change it to the working volume and have the minimum and maximum working volume that they are interested to know, the mixing duration or other parameters that they are interested in, and type in the agitation rate that they got from the previous step. And to ensure that these are the worst case scenarios that we want to see in this tank, they would go to the extremes of higher density and viscosity for the fluids inside the tank. So again, after running the program, they would get this type of results that they would understand at each working volume what is the expected or required mixing time for having a homogeneous blending of materials inside the mixing tank. So as a recap, we at Amgen, we have successfully developed a comprehensive model for various mixers. We have qualified the process itself, the workflow that we have in place. We have introduced an in silico guideline for the users to use and also get insights from the app. So it enables the simulations for every engineer across the Amgen that can have access to these results and get an insight on the mixing tanks. Here I should acknowledge all of the efforts that was done by all team members. I'm part of the team members here, as you can see, at TDC at Amgen. And thank you all for also participating. I'm open to any questions from the audience right now.
Thanks, Masoud. There are a few questions in the Q&A in the chat. I'll just ask you, could you please share the process for development of this democratized app? What is a realistic timescale to build this? How would IT be involved?
Yes, of course. That's a great question, actually. Like the whole thing is automated, as I mentioned in the presentation, and the workflow is just one click. We just need to provide the CAD files, and based on the number of CFD runs that it would need for getting to a certain level of error, it would run the system by having an on-demand and also AWS, which is capable of using GPUs. And M-Star, thanks to M-Star, it's very quick, and we can get very high number of DOE simulations for the process optimization, as I mentioned here. But typically, less than a couple of days, we can have a surrogate model generated for each tank. And so the IT department is going to be involved mostly on having support on AWS and for having a high performance computing or HPC type of system for this workflow to deploy it on.
Okay, next question is, what type of on-demand AWS GPU have you used for the web app?
So yes, I need to get back and get those details, but we have enabled different types of GPUs from Tesla type of the GPUs to other types. But since we are capable of running them in parallel, we just need to have the cheapest type of GPUs that is available by the AWS, and it can sufficiently boost the process itself because they are running in parallel.
Okay, and the last question, how many users would you guesstimate currently, use this app across Amgen?
Of course. So we have right now champions throughout different sites of Amgen that they have used it extensively, and they were pressure testing this tool. We are going to have a launch and learn very quick in near future, and it will get more traction. But right now, we have identified like 2 or 3 champions throughout different sites of the Amgen that they are routinely using these tools. But for them to fully democratize it, we need to have more launch and learn for the users, for the other users to have more traction with the app.
Okay, I think that wraps it up. Are there any other questions for Masoud? All right, thank you, Masoud. If you want to, thank you so much. If you want to give a closing message, or
yeah, of course. Anyone, if they have some questions, I can answer them through the chat as well. Appreciate it.
Okay, great. Thank you so much, Masoud. All right, just want to let our audience know we have come to the halfway point of this symposium, and in honor of that, I would like to mark the moment with a joke courtesy of ChatGPT. John, I'll just direct this one at you because we need someone to answer the joke.
Oh, fire away.
Okay, get ready. Why did the particle get a speeding ticket?
I have no idea.
Because it couldn't resist going with the flow.
Oh, that's a pretty good one, like a low Stokes number and stuff.
Yeah, right? I mean, it's amazing what AI can do.
It is. That's a good one. I like that. Yeah, but it's a good joke. Like only if it's a low Stokes number particle, right? Because then it's going to fall out of the flow, have a path line. So
Yeah.
So gotta wait till ChatGPT, a couple more generations, and we'll be.
Yeah, they'll be funny in the future. Just wait, just wait. Okay, folks, we are moving on to our third presenter, Reza Ebrahimi. Reza is a principal process modeler at Bristol Myers Squibb. He is a member of the Integrated Technology and Engineering, the IT&E team, which is under the Drug Product Development Department. Within IT&E, he employs various simulation tools to guide the processes, optimize them, and also help troubleshooting. He has an MPhil from the University of Sydney and a PhD from the University of Edinburgh. So, Reza, we turn the time over to you.
Okay, thank you very much. Can you confirm if you hear me okay?
Loud and clear.
Perfect. Okay, thank you, Amber, for the introduction and for the opportunity to share our experience regarding developing and also deploying CFD to non-CFD users at Bristol Myers Squibb. And thanks everyone for taking the time joining this meeting. As Amber mentioned, in IT&E, we use various modeling tools and techniques, and one of the simulation techniques that I regularly use in my role is CFD. And as I said, today I'll try to share my experience regarding developing and also deploying CFD models. I would say my presentation structure is pretty similar to what Cory presented, but I can share my experience as a customer who has actually used Aeroflow and M-Star. And yeah, so I start with background and vision. First, I would like to tell you about the idea that why we think that using web apps help Bristol Myers Squibb. again, as I mentioned, we use different modeling tools in my department. And one of the very active domains that we regularly use modeling for is oral product development, when we simulate powders and we simulate actually powder flow to make tablets and capsules. We have developed apps for different unit operations and processes in oral product development domain. And we have shared those apps with non-modelers at BMS. And based on my observation, I can tell that in the last few years, the use of those apps has been steadily increasing. And now those apps are actually part of the standard and routine procedure for non-modelers throughout at BMS, that they use those apps to investigate the tableting and capsule filling and so on. So after that successful deployment of those apps for OPD domain, then the question that we ask ourselves was that when we have this successful experience, can we actually promote CFD and create some CFD apps that we can then enhance the use of CFD just from a group of skilled SMEs to a tool which is accessible throughout our company. And just moving from really SME CFD team to enterprise CFD team. At this stage, and at the moment, usually what we do for CFD projects, project leader or technicians usually identify the issue. They contact the SMEs from different departments, and they discuss the project with SMEs. We allocate the resources and perform the simulation. The work is completed by SMEs, and we deliver the project to or CFD to the project team. What we are trying to achieve is just moving, as I said, from SME CFD team to enterprise by just bringing the end users actually to help us with running the simulations. It is not necessary, I should say, that to develop CFD apps for all applications, but we believe that there are some, I would say, routine and repetitive tasks that we have that actually developing apps for those applications can make sense. Yep, I just mentioned that we have some tasks that we believe using CFD apps can help the CFD team to deliver the project faster. And again, I believe it is not really cost effective to allocate CFD SMEs time to perform some repetitive and somehow relatively simple project that we already have very well established model for. Just sharing some of the solutions that somehow we can use and we are currently using it at BMS. You know that you can create some templates or scripts and push your simulation to cloud. And again, through scripting, you can extract the parameters of interest. Or some softwares come with some capabilities like parametric analysis that, for example, you can define what exact RPM range you want. This software runs all the cases, just return the results, and CFD SME actually can review them and make the decision. Or some softwares come with batch mode running, which in fact you have a text file with different conditions. You can run them and get the data back. However, we believe that those are improvement, but not the ultimate solution that we are looking for. They are not that easy to use, and they are not accessible throughout the enterprise. And sometimes you also need some training to be able to use those capabilities. What we think is the final solution is the web-based apps. And that's actually when I started talking to John and Cory and Seb from Kitware to explore opportunities and gain a better understanding of what we can do together for web-based apps. Advantages, since Cory mentioned some of them, I'm not just going through all the points, but two important ones that I can highlight here is one is that I mentioned when we create these apps, pass it to end users, then it enables the CFD team to focus more on novel applications rather than repetitive works. And another one that I wanted to share is reducing the project delivery time to our partners in the organization. Usually, the timeline for CFD projects is decided by the CFD SMEs, and if, let's say, I'm busy with another project, I will ask the project lead for some extended period of time, and it can delay the project delivery time, and at the end, it causes some delay for the entire project. But when we create the app and pass it to the end users, it helps that they decide actually when they want to run the case. They can explore different scenarios, and they can decide on the best and optimum process condition for their process. So I really believe it helps to shorten the project delivery to the partners. Also, similar to what I explained for OPD apps, using CFD apps at BMS, I really think it helps us to pave the path for future app-based models. And based on the capabilities that I have seen from M-Star and also Kitware, I'm really optimistic that we can deliver on the apps for CFD. And based on this success, we can work on more app-based simulations. Something else to share with you guys is just making this apps. Obviously, we needed to work closely with our IT and also the end users. What you guys are seeing here is what I actually communicated internally at BMS to set the expectation and also clarify each team's role throughout developing, deploying, and using our apps. I tried to summarize the role of each team here. Obviously, the SME is the responsible and model owner and is the person who creates the app. If any changes are required for the app, again, if someone comes to me and says on top of sheer stress, I would like also to know what is the depth of the vortex. I'm the person who adds this capability to the app, compile it, and then deploy it and share it with the end users. IT plays a big role in enabling this capability. We got some support from our IT in terms of providing the proper resources required for each app, also facilitating the access for the end users to web computing. And end users, obviously, they are the people that at the end will use the app. And that's I would say the beauty of this approach is that we are involving the end users also in running the simulation. They are the people with hands-on experience, so we work closely with those people to define the range of the operating conditions, also deciding on what input parameters should go in the model and what exactly they expect to see as output. Again, updating the app is pretty straightforward, as Cory mentioned, and based on my experience, and I will show just one slide how it is done, but changing the input parameters or getting the output that you would like to see from the app is pretty straightforward. Again, as I mentioned, there are some repetitive and recurring projects requests for the CFD team that at BMS we thought those applications can be the first, I said, proof of concept or candidate for developing apps for. One is dilution, another one dissolution. I tried to write it here. What are the objectives for each app? In dilution, you want to find what is the time that we get into the homogeneous state for buffer and drug substance. And dissolution, we have a solid or API that we want to see how long it takes to dissolve it in fluid. The equations, everything you can find in John's paper also in these thesis for these two applications. But these are, as I said, the pretty standard CFD requests that we get in drug product development. So I work closely with Kitware and also with M-Star to develop these apps. They're just like, you just need to change some parameters in the text file. Cory and Seb from Kitware shared some, I would say, tutorials. I went through them for a few hours, and I would say less than an hour, I was able to develop the first app that I later on shared it within BMS. But it is pretty easy to create the app, and that's what you as an SME see. And here you can see the deployed version of the app to the team. And here you can just see the snapshot. Unfortunately, I cannot show the live demo, but I just tried to get the snapshot of the apps that currently we have at BMS. For dissolution and dilution, there is some information about the app, and also it is pretty easy for the end users to change the parameters, run the case, compare the cases. When I presented the app inside in BMS, I got some feedback. I shared that feedback with Kitware, and they quickly enabled those capabilities in the app. One was, what if we have design of experiment, or another case was that if we want to connect the app into the library of geometries and systems that we have, how it works. I'm working currently with Kitware to also enable those capabilities in the app. But yeah, as I said, it was pretty easy to work with M-Star and also Kitware to implement the changes that I wanted to see in the app. We talked all about the positive things, but there are some consideration also, I would say, when I introduced this capability at BMS and tried to promote it. One is the willingness of the end users to adopt the new techniques. The best way, I think Masoud also talked about, is to find some super users or tech-savvy people. I'm working with some people from different departments that are interested in using new technologies, and they are actually my champions, and I'm working with them to promote the apps at BMS. I said it's pretty easy to develop those apps in Aeroflow. However, still compared to some OPD apps, they are more complex. There are some considerations in terms of accuracy of the model that obviously the SME needs to check. But all in all, it is pretty straightforward steps for developing the apps. Licensing is something that I have talked to John, and I saw that Masoud talked about some licensing structure that hopefully we can also leverage and use. And there are some items that I believe can improve the app capabilities, like creating the automatic report generation. I know Kitware already has a solution for it, but I believe it can be improved. And finally, again, I wanted to emphasize that those apps are not just replacing SME's experience. It is just reducing the load for CFD team and getting other non-modelers also involved into modeling and simulation, and bringing modeling first mindset into BMS rather than always relying on experiments. And by that, that's it from my side. If you guys have any questions, I'll be happy to answer.
There is a question in the chat. Thanks for your talk. Thanks for your talk. Who keeps an eye on the created data? Are simulation results permanent or discarded after reviewed by the user?
At this stage, we keep all the data, but you or the end user, I would say mainly the CFD SME, because you still need some understanding of the structure of the data. I would say SME is in charge of data at this stage, but it would be possible to share it also with the end users.
Any more questions? If you have any more questions, please pop them in the chat. Okay, well, Reza, we'll leave you to close up and we'll move on. Okay, thank you, Reza. We're on to our final speaker. You guys, we've made it. Good job on a hot summer day. I know it's a hard time to be inside staring at your screens, but you guys have kept it up to the end. Bravo to you. We will now introduce our final speaker, and just also want to say again, thank you so much to Cory, Masoud, and Reza for taking the time today to share this really great new emerging technology that helps all of our end users. John Thomas is going to be our final presenter. John is the founding president of M-Star CFD, overseeing all client support and engagement. Prior to M-Star, John was a research professor at Johns Hopkins University. He holds a PhD from Carnegie Mellon University and an MBA from Georgetown University. Take it away, John.
Yeah, hi guys. Thanks so much for being here. Let me make sure my screen is sharing the way I expect it to share. Folks can see my presentation. They can see a title slide and whatnot, I presume.
Looks great.
Thank you. All right, I have this kind of cheeky title, Running CFD Simulations on Your iPhone. I should have called it From Your iPhone, but I think it gets the point across. This is something of an amalgamation of what was spoken about in the previous talks. And the point is that we're looking for ways to get simulations in the hands and laps of more people, right? How can we get it out of the CFD engineer's laptop or HPC and into the place where the actual end user can use it and engage with it? There's a couple kind of threads that have come through here, and some people have said them explicitly. I think they're worth kind of rehashing. Is that the further the simulation result is from the end user, the more likely it is to be somewhat not corrupted, but muddled, as it were, misinterpreted. Said again, the further the prediction is from the person that's actually going to use that information to make an actionable decision, the less likely that information will provide action to the end user. I'll explain that in a minute here, what I mean by that kind of little tautology, but I think it'll become clear. Second, one kind of unsaid comment here that we've been going through as we're going through these talks is this idea of like running these codes really fast, getting the simulations to solve quickly, making some of a real-time execution, folks have been saying. And I always start with this, and I'll start with this point just to begin with. It's all about GPUs. Yeah, and I know this came across in Masoud's talk of what sort of GPUs he's running on AWS, but I want to just emphasize this point to begin. Is M-Star doesn't even run on CPUs at this point. We've burned the boats, okay? And this isn't again, Burger King versus McDonald's type of argument. The amount of functionality to get out of a GPU would require hundreds of CPUs to reproduce in terms of flops and the bandwidth capability. And so foundationally, why can we do this? All about the GPUs. And again, these are just raw numbers coming out of performance in terms of math and memory transfer. And again, you convolute these two, and a good A100, a good V100, even a good A6000 will have the comparable functionality of several hundred CPUs. And they'll achieve that with one PCI slot in your desktop. And so foundationally, that's what's going on behind the scenes. So this kind of emerging hardware has really revolutionized how we can approach simulation, the speed at which we can run these simulations, and the fidelity we can access and give the users. Again, this idea of doing a time-accurate three-dimensional LES simulation from an iPad, right? Accessing, again, a GPU resource. Like, how was that possible? It's all about these resources behind the scenes. And in fact, this emerging technology, just to briefly editorialize here, this isn't just a simulation thing. Like, why is ChatGPT, this terrific comedian, why is it a thing now? Well, it's the hardware. That's why it's a thing. Like, why did the self-driving cars come about, or the autopilot in 2016ish or so? It was the V100s. Like that's what motivated. It was the hardware, as it were. Yes, we're developing new algorithms, but are these tectonic changes in hardware that's available to us that's motivating big changes in how we live and compute. And those tectonic changes are not isolated to non-CFD things. They're changing this dramatically, as it were. So let's kind of jump into kind of how, and I'll just jump into something live. I had this pre-canned, but let me just jump into it live. Like, this is how engineers work now in a lot of cases when doing simulation. This is M-Star. They get a task. Someone comes in the door and says, hey, I need to be able to predict NJS, or maybe a resonance time distribution, or blend time, or a KLA inside this vessel. Can you predict that for me? So the engineer gets the task, and he or she goes, and they'll go ahead. I'll just kind of skip this process here for the sake of brevity. They'll go through and build their model, right? They'll go here, and maybe they'll have some CAD. Maybe they pull it together, and voila, they've got some model here, and they're going to predict strain and EDR inside this vessel. So they've got some strain rate dependent process going on. So the engineer gets this. He or she chooses an appropriate resolution and time step. The engineer hits go. The engineer runs this, and this is, again, M-Star just kind of cranking on the desktop as most people might use it, Windows machine, and they hit go, and the code runs, and it starts marching through time as it is here. They'll go to post-process it and visualize the results. They'll down-select the results and make a movie or whatnot and begin to show what's going on across this vessel, right? They'll maybe make movies and get some output here. They're going to show us what's going on. Maybe they'll generate a plot. Like, this is great. And they'll spend time doing this. They'll spend time aggregating this data, and they'll make the results and go back to their client, right? And their client then says, well, what if I change the impeller speed 30 RPM, right? Or what if my viscosity changes from, instead of being water-like, to some non-Newtonian honey-like fluid, or some sort of bioproduct, as it were? What if these particles I'm trying to suspend in crystals are a bit heavier, right? What if their size distribution is different than I expected? And the engineer takes that task, runs back, reruns simulation, gets the results, and repurposes these back to the client. And so it's a fine workflow. Everyone's kept busy and gears are turning, but foundationally it's an inefficient workflow. We have someone with advanced degrees in physics rewriting the same model over and over and over again. Yes, it's good that he or she has the ability to kind of understand where the nuances lie in terms of numerical aspects, grid spacing, time step, etc. But once you're running that model repeatedly, you have those guardrails pretty well set. And at some point, you're changing operating conditions as opposed to numerics. Once you're getting to that point, once you've kind of stopped doing the math and are strictly changing the operating conditions, that's where it starts to become inefficient for the CFD engineer to be operating, and it's more efficient for the process engineer to be getting that data themselves. Let me go ahead and go back to this screen one more time and kind of speak to this point. So again, what we want, what we want are for engineers to be able to, I should say, end users to be able to use and access these simulations on their own without having to iterate with the CFD engineer every single iteration. So what are the barriers to this? What stops us from just putting M-Star on every computer in the enterprise? First, the code is easy to use. It's easy to use. We can't kid ourselves. Like, it's not hard to build M-Star models. But there is some thought. There's still like a lot of parameters here, just empirically. I've got to specify rheologies of course, and choose like my turbulence model, LES versus DNS. There's still some executive decisions that have to be made There aren't a lot of decisions, but there's still engineering and numerics that goes into building this model that a chemist may not want to know, understand, or care about. Like, does a chemist really care? Like, whether you're using implicit large eddy simulation or large eddy simulation? Like, they kind of do, but not necessarily. That's more of a decision for the CFD engineer, the numerics guy. Does the biologist really care what flux limiter they're using? They may not even know what that term means. To the engineer, it means a lot to us. But if we find an appropriate set or find an appropriate condition, they don't need to be retooling that every time they want to change an impeller speed to see its effect on vortex, or maybe glucose distribution as part of a cell growth process. And so again, I'll maintain this point. The code's easy to use, but we could still tailor it. And I think Reza showed this for people that are looking for specific variables. Second, the software is very lightweight, right? M-Star doesn't take a lot. It's not a huge program, as it were, but you still got to get permission to install it, right? And that's typically the biggest barrier to using a new software. Isn't the code, but it's the IT permissions. Second of all, I made this point. The hardware requirements are modest. You don't need a monster GPU, but we still need a GPU. And there's still like a special thing for some organizations to procure. Like, they have to like make the decision that they're going to go buy a GPU, as it were. It's not as available as just everyone's laptop. And so the code is easy, the software is lightweight, and the requirements are modest, but yet there are barriers here. And so we've been talking about this throughout the day, but like, what do we want? Like, we want reduced order applications that streamline the import, export, and reporting. We saw this. Reza, he took all my thunder, which is great. I'm glad he did. But at the end of the day, they want to interact with something that's reduced order. A second, ideally, and this is what Masoud was speaking to, we don't want engineers having to install things on their own computer. Cory spoke to this point as well. Everything's web app these days. Okay, everything's a web app. All right. And it makes much more sense from a democratization standpoint and an accessibility standpoint. People can do these things through a web app or their phone or iPad. We still need the hardware, of course. This is to get around that, but not everyone needs a GPU. Everyone just needs a web browser at that point to access what would be served up by the GPU, and that does simplify admission. Let me talk about this briefly, kind of from a business standpoint as well. And and maybe I'm getting a bit too cheeky here, but I think this is like a worthwhile point to speak to as a business and us as engineers kind of managing our careers. So this is what we typically have. We have scientists that come to us as modelers with tasks, right? And I eliminated a few, like, what is the blend time? What is KLA? What is dissolution rate? That's work. And if we have a broad number of scientists ask us for tasks, we're like a well-employed engineer. We're like a good consultant to the firm. So we take these questions, and there's going to be information loss, but as they kind of like describe what they think the viscosity is, as they say what they think the vessel looks like, as it were, and we're going to go into this literal like black box relative to them to just create magic. And we come out of this black box, out of the CFD system with results. And in some sense, guys, not to be too reductionist, we sell our results to them, right? We sell our results. We say, good news, the black box relative to you told us this, money, please. And they like it. They get good results. It informs them, as it were. Whenever they have a perturbation, whenever you get a new user, this person starts to collapse as they get more and more demands on their time. They do good work, so more people come to them. They start getting tasked with possibly more rote tasks, I should say, as one scientist asks for more iterations on the same simple system. And so the problem with this is that the modeler is working in the business, okay? And you don't want to work in a business, okay? You want to work on a business, okay? So that's the business. This is the business, and this has some sort of revenue and some sort of cost, and that cost offset by the value provided to the scientists. Again, none of us are going like no one at Pfizer or BMS or Amgen is starting out thinking, the CEO is thinking, what CFD can I do today? The leaders are thinking, what drug products can I make? And CFD is a tool to make that happen. And so foundationally, we're seen as some sort of business within a business, not the point of the business. What do we want? We as individuals, and even as CFD folks, we don't want to be in the business, we want to be on the business. And this has two benefits. One, it lets us scale, and two, it helps our enterprises scale. What we want to be doing here is giving these scientists tools they can use directly that A, get them right to the physics, as it were, without them having to reinterpret what the operating conditions or viscosity or topology should be, and B, allow them to iterate, right? Give them a tool that allows them to cycle through the impeller speeds, the gas flow rates, the oxygen uptake rates, the inlet outlet the velocities as important resonance time, as it were. And so foundationally, and what we're doing as the engineers is we are developing the apps that they can use. So yes, necessarily, this doesn't require us to stretch a bit. It requires us to learn a little bit of not only CFD, but also some of this app development. So there is a stretch that goes into it, but importantly, this is made very frictionless now with tools like Trame and Aeroflow. I'm mentioning, Cory, the open source component. I know Aeroflow is buttoned up and easier to go. But this is an important point, guys, is that, it's better for us as engineers, like professionally and as a business, for us to be working on the business, not in the business. When you're working in the business, you just kind of like fill up, and then we have to have another unit U to take on the more tasking. When you're working on the business, you're creating something that's deployable and that's scalable. You're becoming the wires in the wall, not just the painting on the wall. And you want to be the wires of the painting. And so foundationally, this is what we're trying to do. And really, Tram and Aeroflow make it possible. And it's not, and I think Reza spoke to this point. Yeah, you got to learn a couple of new skills. You got to learn to write some of these new configuration files. But these new skills, these new files, this new ability to kind of convert model to app, hours is really the investment it takes to make this happen. And what's the value? Hours of saved time, right? When you're not running 50 blend time simulations or 13 RTD characterizations, as it were, that frees you up to work on more interesting problems, as well as create more apps for more scalable deployment. Okay. I think that's kind of an interesting point to make, just as we kind of go through it. And again, this sort of deployment can take a variety of forms. And here is where I'm going to make good on my claim about CFD on the iPhone. And this is what people are doing. Like, imagine there's a QR sticker just stuck on the vessel, as it were. An engineer goes up to it, or a plant worker goes up to it and says, you know what? What's going to happen if? And those are great questions to ask. Like, when a lab technician or an operator can say, what would happen if? And they can immediately answer and explore that question. That's where innovation happens. Where innovation dies is when it says, oh, I could never test that out. Or I know some guy at corporate CFD that might be able to help me, but it's not worth their time. But foundation, when you can put these models in the hand of the users, like, that's where the action happens. And so if you want to, we're probably going to crash the server. Go for it. Like, scan it if you want to and click on it, and you'll see, like, your connection is probably, everyone's going to crash it. Maybe do this at 2 a.m. if you want to. I pre-recorded it. But like, if you like, this is what goes on. Here's me scanning it at the end of the day, and you're launched into it. And so foundationally, like, this is lowering the barriers to entry, as it were. But you can have the plant engineer, right? Interact is loading. I apologize. This wasn't a super fast server. But like, when he or she's able to go in, click on their simulation, adjust these workflow items. I'll skip through in the interest of time, as it were. View results. We can interrogate what's going on. Like, that's where the action happens. When the CFD engineer, with appropriate guardrails, of course, like, and these things are defined with the guardrails to prevent them from modeling, so it's outside the bounds of the numerics. When he or she can start to do this investigation, understand what's going inside the process, this short circuits so many calls, as it were, to you, when they can make the discoveries themselves. And that's the point here. The point isn't just running more simulation for simulation's sake. It's about getting the tools in the hands of the users that can turn that into something actionable. Okay. As we kind of go through this, I got a few more things to illustrate. And again, you're welcome to try it. And again, if you're trying it now, I apologize, because there are probably 57 people trying this, and the server's going to weep, as it were. So you can have these slides later, so you can scan this yourself. And I'll be brief here. But there's a reason why I made these videos beforehand, because I knew it was going to be crushed. But again, this is the important point. Is like, here's an example of that same kind of a dish bottom tank, I should say, conical bottom tank. This time with the user investigating different sorts of, oopsie, my slides are moving, not my movie. With the user investigating different fluid fill levels. And it's amazing how much you can learn within like a simple simulation. Like, why did my process not aerate properly? Why did I get too much oxygen? Why did my particles not suspend? when a process engineer can see, oh, my power peanut volume is way too high, or oh, my blend time was, it's not a mixing problem because my blend time was 3 seconds. This would be some other sort of problem with respect to maybe process control. Like, it's amazing how empowered they can be to optimize a process where they can answer their questions independently. Let me click. I'm trying to be brief with my slides. I tried to have an elastic presentation here. So again, the point is this, is that, let me go ahead and jump through just to where we are, because we're almost at time. I'm going to start off with the way I started. The code's easy to use, but like, it's still hard enough where a lab tech might not do it. So if we can create reduced order apps that get these in the hands of the lab tech, of the hard hats, of the plant operator, as it were, we're immediately providing value to them. The software is light, but it requires any permissions. Apps avoid that. A web-based deployment anyone can use. Yeah, maybe you got it behind a firewall because you want the world walk into it. That's fine. But foundation, that's a solvable problem. But the important point, this is doable. It's doable now. This isn't like some idea. This isn't some dorm room pontification. People are doing this now. And the value that comes with getting these tools in the hands of end users to be able to make informed decisions within the walled gardens is beneficial to everybody. Them, us, scalability, careers. Yeah, it's something we got to do. Okay, I'm pretty much at time. I want to leave a few minutes here on the back end for any other questions. Again, thank you for being here, folks. That's kind of the big picture, the thoughts. Thank you to the intermediate folks who gave top solution application. But yeah, happy to take any questions about this and workflow and other kind of, I wasn't too cheeky with the whole like career advice, work on, not in a business, but it's true. It's true. Like, if we want to really do well as engineers, like, we don't want to be just turning a crank. We want to be defining like a scalable operation, and tools like this get us there, like much more so than just taking on more tasks. So food for thought, maybe on a line, but happy to debate it. Thank you so much. Yeah, Amber, back to you. Thanks. I'm at time, I think.
Thanks, John. That's great. Your enthusiasm is inspiring and infectious. I feel like I just want to go create a simulation right now. And I don't even do that. So that would be amazing. But with Kitware, I probably could. So even for beginner folks like me. So thanks so much to everybody, to Cory, Masoud, Reza, and John for your presentations on enterprise deployment of CFD models. Your expertise has given us a deeper understanding of what is possible using browser-based solutions and apps that will make CFD simulations more accessible, scalable, and deployable. Also, thanks to all of you in our audience who have taken time out of your day to join us. I want to inform you that this webinar has been recorded and will be available to access soon on our website and our YouTube channel. That's mstarcfd.com, and on our YouTube channel at M-Star CFD. Please reach out if you have any additional questions, and have a great rest of your day.
Thank you.
Thanks.